the other teeth, right? Every time. So if there is imbalance in the shaft, you not only see the main gear mesh frequency, you may also see what we call side bands. These side bands. So a side band is essentially the difference between the gear mesh frequency and the shaft frequency. And if this side band increases, okay, so that indicates you have too much heating caused by imbalance in the shaft. So these are common frequencies. If you have a pump or a fan, as the pump with so many pumps have vanes or blades, right? Blades. And we have fans have 3-4 blades. So when the fan or pump rotates, the blade is going to push the fluid, whether it's gas or water, fluid, doesn't matter. So it's going to push it, and there is a pressure, transfer of pressure onto the fluid, right? So you may see in a pump or a fan, you may see frequencies at what we call, at values corresponding to their so-called vane pass frequency or blade pass frequency. So what is blade pass frequency? It is the number of blades or vanes on the pump times the rotational speed, right? That should give you vane pass frequency or blade pass frequency. These are common. You may see them even in the pressure signal. If I'm measuring pressure, fluid pressure, that fluctuation gets transmitted to the fluid, and you may see that in the pressure sensor at that frequency. Kind of interesting. You can indirectly measure the effect on using the pressure sensor. Example, it says a 6-vane pump rotates at 1170 RPM. Okay, what is the blade or vane pass frequency? 6 times the main rotational speed, about 117 hertz. I have that comment that this frequency may also be seen in a pressure sensor. If I put a pressure sensor in the piping, you may see those fluctuations in that frequency. Okay, so that's so much about pumps, gear drives, belt drives, and bearings. Okay. Any questions? Do you have any questions? After the class, you can, if you want, you can take a look at these wireless transmitters. The last part of this presentation has something to do with vibration in reactor system. This is a, I don't know how many of you are familiar with nuclear reactor systems. So what you're seeing here is a so-called pressurized water reactor. This is a in a pressurized water reactor. You have the reactor core inside, somewhere here, and the water flows up through the core, it gets heated, and it comes out. Okay? So you have water may be entering the core at about 550 degrees Fahrenheit and leaving the core at 610 or 615 degrees Fahrenheit. So you have a difference in temperature between the inlet water and the outlet water, about 60 degrees Fahrenheit. It's kind of common number. So in this case, the water, of course, the water is going to leave, the water that goes up through the core is going to leave through the hot leg, it says here, hot leg. Where does it go? It goes to the steam generator, right? In the steam generator, the heat from the primary water gets transferred to the secondary water, or the water coming from the feed system, and you generate steam, and the steam comes out at the top. Okay? So this is the so-called steam generator. This is fairly long, right? It's about 60 to 65 feet tall. whereas the reactor vessel may be about 45 feet tall. So it's almost 20 feet taller than the reactor vessel because of the tubing inside this. So when the steam comes out, you want to make sure the steam is almost 100% steam. You don't want any water in the steam. This steam is saturated steam. There is a lot of water being carried out. So there are steam separators at the top that remove the water from the steam, and moisture separators, so removes any leftover moisture. So you have almost 100% steam coming out of the steam generator. So then the hot water that goes up to the steam generator and comes back. Okay, this is one of the, right here, comes back from the bottom, then it gets pumped back to the reactor vessel. So those pipings are called cold legs because the water is colder than the other hot legs. So when the water comes in, you notice there are 4 of these. So the water is coming from 4 pipes into the reactor vessel, right? Into the reactor vessel, and inside the reactor vessel you have all kinds of reactor internals. You have reactor core, you have fuel elements, control rods, you have what we call thermal shield. All these things are going to vibrate, and why do they vibrate? Because you have, what's the reason they vibrate, you think? Because the water is coming at fairly high flow rate into the vessel, and it's going to hit this reactor internals. The total the total water flow rate through this system is about 120 million pounds per hour. That's a lot of water being pumped into the reactor vessels. There are 4 pumps, of course. They all pump together 130 million pounds per hour. So that causes some forced vibrations. Not too much. It's always there. So you want to make sure that vibration is within limits. So this is kind of a cross section of what you see inside. We have the water coming in, water leaving. This is the reactor core. Reactor core is supported by a core support barrel. This is the so-called core support barrel. And notice the core support barrel is, of course, it is supported at the top and also it is supported at the bottom, but it is almost like, it moves like a pendulum. So when the water hits, it's going to move around a little bit. Okay? And even though it is anchored and everything, it still has a little bit of motion. So you want to measure that motion. It talks about core support barrel vibration, about 5 to 10 hertz. It's like a beam mode vibration. You can have a shell mode vibration of this structure, right? Shell mode means you're squeezing. When the water hits, it may get squeezed a little bit, not much. So that's the shell mode vibration. Then there may be other frequencies. The basic pump speed is about 20 hertz, 19.8 hertz. So how do you measure this vibration? Generally, we don't put any accelerometers. So you can measure the vibration by measuring the change in the neutron signal. There are detectors outside the vessel that detect the change in the neutron signal as the core barrel moves back and forth. When the core barrel goes close to this side, you get a higher signal. When it goes away from it, you get a little bit lower signal because of this pendular motion. So you can measure those changes, what we call neutron noise or neutron fluctuation in the signal. Very small. That fluctuation may be less than 0.5%, even less than 0.5%. Very small amount of variation, but it is large enough that you can use it for monitoring core support barrel, control rod vibration. Control rods are used to control the neutron population inside the core, fuel assembly vibration, and so forth. There is another type of reactor called the boiling water reactor. This is pressurized water reactor. Boiling water reactor is a little bit different inside the reactor vessel. There are a lot of instrument tubes that could move or hit. You can also measure the impacting of instrument tubes. This is how the signal may look like in a PWR versus in a boiling water reactor. Notice the fluctuation in the PWR is small compared to that in a boiling water reactor. Boiling water reactor is more noise because of boiling inside the reactor vessel. If you compare the two, you can compare the frequency spectrum of the signal. This is energy versus frequency. The lower plot is for a PWR. Notice it has these peaks because of the vibration of those internals, and this is the boiling water reactor. Boiling water reactor has a higher noise, so the percent noise for a BWR is higher than for a pressurized water reactor. That's expected. So this is how the detectors are placed around the outside the reactor vessel. This is the core of the reactor vessel. There are 4 sets of detectors. If you go to Sequoia or Watts Bar, TVS power plants, you see, don't see, but they have these long detectors in the biological shape. So these are the detectors, top and bottom. There are 4 sets of these, okay, around the reactor vessel. So all of them should give you kind of similar signature. So this is just showing what I mentioned earlier, beam mode vibration of the core barrel going back and forth across from these 2 detectors. It's pretty good. You can measure the change with those detectors. This is the shell mode vibration. This is a little bit exaggerated. You don't get that much squeezing of these. Very, very little. Okay. So if I take those 4, 1, 2, 3, 4 detectors and process the data, okay, this is what you see, the spectrum, the energy spectrum, energy versus frequency. Notice all the 4 have similar behavior, right? And they should, because it's symmetric, everything should look similar. Now if they don't, that means you have some problem with the core barrel moving more towards one detector than the other detector. There could be some other type of vibration in the system. This shows same one of the plots. So this range here is about the core support barrel vibration frequency, and around here you have the thermal shield vibration, that is the pump frequency, and so forth. So it's about, goes from 0 to 50 hertz. So what you're going to do with this plot is you kind of monitor how this changes during the fuel cycle. So if this increases, if the energy at these peaks increases, that means you have more vibration happening. So maybe something is not right. Maybe something is loose. So there could be reasons why the spectrum is changing. There could be some normal change during the fuel cycle, but if it is beyond the normal change, then you have to worry about the mechanical, structural integrity of the core. That's the whole idea here. Monitor vibration. Okay, just a few comments. Most of the vibration that I talked about, you may say they're coming from low frequency vibration or low frequency machinery within maybe 3,000, 4,000 RPM. There are other forms of vibration modes. These include high-speed gas turbines or steam turbines, vibration of aircraft wings, helicopter gearboxes, heavy machinery. When I say heavy machinery used in mining, excavating large amount of drilling, So these are a little bit different, right? They may not be high frequency, but they are different types of machinery. So the whole idea is to minimize the downtime. You want to make sure the system is not down because there was some problem with the operation or with the different components that support the machinery. So the cost of system downtime is very high. If it is a nuclear plant, if the system is down, you lose about $1 to $1.5 million per day. If it is Alcoa here, and if the system is down for a day, they lose revenues equivalent to making 75 million cans. That's a lot of sheet. Of course, the sheet is very thin. That's a lot of sheet they're going to lose. Revenue. There's a lot of revenue, right? So you have to worry about unanticipated downtime. Of course, there is downtime when you go to repairing or maintenance. The goal is to monitor vibrational energies at different frequencies and trend them. I showed you one trend plot, and use that information for detecting any incipient fault. That means any fault that is slowly changing. You suspect something is going wrong, so you want to fix it. So you look for these incipient changes in the behavior, and you can accordingly plan either maintenance or repair or replacement or whatever you have to do. Okay. So that is the whole idea behind monitoring the machine, in this case, monitoring vibration. As I mentioned earlier, the best thing to do is to combine various predictive maintenance technologies, vibration monitoring, blue wire monitoring, maybe temperature monitoring, temperature, infrared monitoring, and things like that. So you need to fuse the data. You need to combine the data. Some of the pharmaceutical companies are fairly advanced in their approach to maintenance, because it's important for them to maintain their production line, right? If companies like Eli Lilly, for example, in Minneapolis, they make a lot of pharmaceuticals, or other companies, they are all big companies. So it's important, because if there is any defect in the product, they just have to throw the stuff. So there's a lot of about 20 to 30% of the products they make, they just discard them because they either don't look right or they don't have the right quality, that kind of stuff. Even M&M Mars, all the chocolate candy companies, they discard about 20%, 25% of their product. Maybe it has gone down, but it used to be pretty high because it doesn't look right. Maybe tastes like it, but it doesn't look. Okay, I'm going to stop here. If you have any questions. You have any questions? Yeah.
Talking about those vibration monitors in the reactor, what's the regular average neutron flux at that size?
Okay, when you say neutron flux, it may be about 10 to the 12, 10 to the 13 neutrons per centimeter squared per second. That's the number for, you asked me, neutron flux. So that it's like saying, it's like heat flux. How many neutrons cross a given cross section per second? So higher the, like if you go to high flux reactor in Oak Ridge, is what's called high flux isotope reactor, is about 10 to the 15. The commercial reactors are about 10 to the 12, 10 to the 13. In order of magnitude more flux. That means you have higher, you can see you have higher energy per given volume. Was that your question?
Yeah.
Any other questions, quick questions? Okay, if you have any questions, you can send me an email, or you have your instructor, he can answer any questions you have.
Okay, see you next Monday. Thank you so much.
Okay, thank you. Make sure you review the notes. this
I was literally told not to go to my girlfriend's apartment. And I expect I'm going to have to go there about an hour. So
I will give you the south. Thank you.
Anybody have accelerometer? That's the big one. There was another one.
No. You go there. We have two spots on the line. So it gives cover for the
Oh, here it is.
wait, what?
Nobody wanted to play with my toys here, bro, I'll tell you.
for next Monday, probably come here. Come here. Okay, just come in lab session. Lab session. We start here with some instructions, then we'll move to the lab. Okay. The parkings.
Okay.
And that is lab. Thank you.
So I signed up for Thursday's the tour, no, Wednesday's tour schedule.
Yeah.
But then now I'm doing Thursday instead, so I'm
Yes.
I already signed up for it. I reloaded.
So you sign up for Wednesday tour, but you cannot make next one, then you have to go for Thursday. Just sign, body has a sign up sheet.
You got a library?
Your name on that sheet.
Okay.
The in-class, the 2-hour lab is going to be in class next week, right?
Yes.
Okay. And what was the paper we signed for? Was that the attendance sheet?
That came around in the class?
I know there was one that came around.
Okay,
Here's your attendance sheet. Okay, that's
very
what we were,
important.
that's what we were gonna ask too. We didn't
Yeah.
know what that thing that we signed that you brought around
Was
was.
that another attendance sheet or?
No. I just want to remember some familiar things.
Oh, okay.
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 You believe that?
No, I don't.
All right, cool.
Thank you. You guys want to ride?
Oh, we got this one.
Turns out my car's right
How
there.
are you?
I'm good, how are you?
I'm fine.
And like, I have to drive my train.
Well,
Oh, yeah.
I think I got everything back.
I teach this.
In the future, also one course will be just focus on research.
Depends.
So your department will get another new
We
professor?
already have.
Okay.
Thanks for that.
Yeah, sure.
Thank you again, sir.
Oh, sure, no problem.
Huge help. Thank you.
It's
so
good to
much.
see
Yeah,
you
good to see
again.
you, but
Yeah, very
he is
good.
the Kent Peterson with the Mobius? or-
No, he's with Windrock. The
Windrock.
compressor, reciprocating
Oh,
compressor
okay.
folks,
Uh-huh.
Windrock.
Hmm,
He's been with them for 9 years now.
I see.
Yeah.
I don't see him very much.